and they also want the future to happen quicker. Those people really thrive at Tesla. And so I happen to also, I think, be like that. And so I don't personally mind it. I actually kind of thrive on it. And I love the energy of getting this to work faster, making a difference, and having this impact. And so I really enjoy working with him because he has a way of injecting energy into the system, driving momentum, and he has incredibly good and developed judgment. So yeah, I overall just really, really enjoy working with him.
Sounds wonderful. Would you say you talk with him pretty much every week, or?
Yeah, that's right. So we have autopilot meetings that range from a week, depending on, just how much scrutiny is being put on the autopilot. Maybe right in front of releases, we would have more than a week. And multiple times in the history of the team, it's been every single day. So yeah, on any of those frequencies, depending on what's happening.
That's so exciting. Wow. If we think about self-driving cars, it's probably the kind of most tangible AI concept for the public, because so many people have cars, and it's how their car is going to change because of AI. Certainly one of the most written about aspects of AI research and application in the press. But not everybody really realizes how driverless cars and AI are connected. What is the backstory there? How long have people been working on self-driving cars? And what is the AI role? What is happening under the hood?
Yeah, people have, of course, been thinking about cars that drive themselves for a very long time. Some things are very easy to imagine, but very difficult to execute on, like driverless cars. Some things are not like that. So for example, a cryptocurrency in Bitcoin is hard to sort of come up with. So you won't see something like that maybe featured in as much sci-fi. But driverless cars are something that people have been dreaming about for a very long time and working on for a long time. And I think fundamentally what makes it hard is, right there, you have to deal with a huge amount of variability of what the world looks like. It's basically true that for AI and technology as it is today, the degree of difficulty is proportional to the degree of variability you're going to encounter in the application. So the more scenarios you have to deal with, the harder it will be for the technology. And that's what makes this hard for self-driving cars as well, is that environments out there are quite variable. Maybe on the highway, you're just dealing with lane following, but once you get off the highway into city streets in San Francisco and so on, the amount of things you can encounter is very large, and designing to it is incredibly difficult. And that's where all the action is.
You hit upon variability, right? That's making it so hard. Can you dig a little deeper? Why does variability make it hard?
Yeah, so like I mentioned, like when you're creating these deep learning systems, you are giving them some kind of a specification for how they should act in different environments, in different cases. So hey, this is a cat, this is a dog. And the network starts from scratch. It's not like your human brain that is born into a three-dimensional physical reality where you sort of understand a lot of objects and you come with all this built-in hardware, but then also incredibly powerful learning algorithms so you can understand objects, object permanence, and how the world works. These neural networks, they are made up of neurons like your brain. It's not an exactly correct analogy, and it's misleading. These neural networks, again, it's better to think of them as a mathematical function with a lot of free parameters, 60 million knobs that must be set to get the correct behavior. And in the beginning, the setting of these knobs is completely random. So the neural net is implementing a completely random function. It's doing completely random things, and it's starting basically from scratch. And you have to tell it what to do in every situation. And the more situations you have, the more you're going to have to give it in order for it to do the right thing in all the cases.
So, Andre, when a neural network starts from scratch and you put that neural network on a Tesla, what would happen if it drives that Tesla?
Well, you'll get random behavior when it's from scratch. It will be completely random behavior.
Got it. So it starts not knowing what to do. So you probably don't put those on the cars, actually.
No, you wouldn't want to do that.
And so you deal with all this variability, and you want this neural network to internalize that variability. What makes the neural network internalize that variability? What's the solution to that?
So it looks like we do it through roughly almost brute force ways right now. So if I want the neural network to function in millions of situations, I need to plug in millions of examples or something on that order. So the neural networks do show some ability to sort of interpolate between the examples you've given them. They're not as good at extrapolating, but as long as you sort of cover the space of possibility and tell the neural network what to do in those different scenarios, they have some ability to interpolate between examples, but it's limited. And so if you really have a massive amount of variability that you want the system to perform well on, you actually have to cover that space to a large extent.
How do you get the data to cover that space?
As I mentioned, in this new programming paradigm, there's a bit of designing the neural network and the neurons and so on, but a massive amount of work is on curating these data sets. Fundamentally, you roughly start with some data set and you train your neural network, and then you measure its performance and you look at where it works and where it does not work. Fundamentally, the way you're iterating on this neural network to get it to work is you need to find a lot of examples where it does not do what you want it to do, and then you need to get those situations and you need to label correctly what should have happened in those situations, what the correct label would have been in all those cases. And then you need to put those into the training set for the neural network. And so the neural network is now trained on the previous data set, but also on a data set of where it failed before, but now has the correct label. And this improves some situations again. And then you have to again look at where it's failing now. The faster you can spin this loop of just iterating and curating your data set, the better this neural network will become. And luckily, we are in a position with these neural networks that as long as the data set is improving, there's no real upper bound on the performance of the network. If you have enough computation available for it and a large enough data set, it will find the correct sort of solution to making your labels work. So most of the engineering is on the data set, and primarily it comes from sourcing examples where you're not working yet.
And sourcing examples where it's not working yet, is that when I drive my Tesla, am I sourcing those examples? How does that work?
Yeah, exactly. So it's a great question. A lot of what I do, of course, at work is just curating these data sets, as I mentioned. That's where all the engineering now is. It's not people writing algorithms, it's people collecting data sets. There's lots of things we want to know about the scene, right? So we want to know where the lines are, where the edges are, where the traffic lights are, where the other cars are, whether or not the car door is open on the car, if the left blinker is on, a huge amount of things. So roughly we have maybe say 30 top level tasks, but a lot of those tasks have many subtasks. Like for a car, you may want to know a lot of attributes about it. What kind of a vehicle is it? Is the car door open and so on. So you end up with a huge amount of predictions that your neural network has to make about the world. And now these networks are deployed in people's cars and they're running and making predictions. And then we have to come up with lots of ways to source inaccuracies. There's many ways by which we do that. Maybe one very simple example is if you intervene because the autopilot did not do something correct. Typically when you intervene in a large number of cases, that has to do with an incorrect prediction from the network. So an intervention is a trigger, and we collect some of those images, and then we look at them, and we look at whether or not the predictions were correct and how were they wrong, and that helps us triage, should this example go into what labeling project, and where should it end up in what data set and with what label. And that's how we sort of iterate on the system. But there's many triggers that are active at any point in time. As one more example, if you have a detection of, say, a stop sign or something like that. So you have a bounding box that the computer is putting around the stop sign. And if the stop sign detection flickers, for example, so it's there and then the network says, oh, it's not a stop sign. Oh, wait, it is a stop sign. When you see this disagreement with itself over time, that also is typically an extremely good source of data. So flicker and temporally inconsistent predictions, or for example, disagreements with the map. So we think there's a stop sign, but the map says that there isn't one. So there's lots of different ways by which we gather examples where the network is mispredicting. And for us, it's an exercise of how quickly can you enter those examples into a training set. And that's a huge portion of what the team is doing.
When I try to think about the data you're feeding into the system, how much data is that? I mean, are we thinking thousands of images, millions? What magnitude are we talking about here?
Yep, so we're talking about millions of images easily. It's on that order.
That's amazing. Now, one of the recurring themes it seems in deep learning is large data, but also large compute. Let's say you want to train the autopilot from all that data. You say, okay, I'm going to retrain it, push all the data through the neural network and train it. How much compute does it take? How long does it take to train an autopilot?
What you're getting at is these neural networks are quite expensive to train. So we start with millions of images, and typically what you will see in the industry is most networks train roughly on the order of 2 to 3 weeks. Because 2 to 3 weeks is actually more of a psychological reason for that, is because that's the amount of time that a person is willing to wait for the network to converge and to measure its performance. But yeah, they have to look at a lot of examples, they have to make a lot of predictions, and they have to be corrected on the predictions they're making during the training loop, and this takes a long time. And as you are scaling up the amount of compute available, you can afford to use a bigger network, and a bigger network will almost always work better, but it needs more training time. And so we're in a place where we are, and this is a beautiful place to be, by the way, we are not constrained by human ingenuity and algorithms, as used to be the case in computer vision, because we had a class of approaches that leveled off, and then we were the constraint. But now, human ingenuity is not a constraint. The constraint is the size of the data set and the amount of compute that you have available to you. The algorithm now is known. Everyone knows the same algorithms, and we just need to run them at scale. And we're getting benefits for free just by scaling up the network, making a bigger network, and making a bigger data set. So it's a beautiful place to be because you have a recipe, a template by which you can make progress, and you're just bounded by very concrete, tangible things that you can improve, like the size of your training cluster and things like that.
Where I hear you say that the algorithm's understood, that's true. Of course, it still requires some true expertise in the space to understand those algorithms, but you're right, they're not secret. I hear part of what you're saying, it seems like you are spending a lot of your time on the data itself and a lot less on changing the algorithms. What does that look like? I imagine you have a large team that helps with the data and so forth. Like, what does that look like organizationally?
Yeah, and I think, like, to your point briefly, it's a good observation that the algorithms, it's not fair to say that they're fully figured out and known. I would say it's more true in some domains than others. Like in computer vision, I think we have a class of algorithms that we're pretty happy with for the simplest image recognition problems. In many cases, for example, you're dealing with robots doing pick and place and things like that. I would say algorithms are absolutely much less known. And so different domains will have different maturity of the technology available. I also want to say that it's not the case that we spend zero time on algorithms. It's more like we spend 25% of the time, not 100% of it. And the only reason I typically point it out and stress that is because typically people coming from, say, academia have an expectation. So in academia, when you're working with neural networks,